All right, so this is Learning Guide 6, Related Rates. This is Lesson 1, where we're going to do an introduction into position, velocity, and acceleration. And now basically what we're going to be looking at in this learning guide is how derivative actually helps us in a real-life situation. So we could be looking at a particle movement, and we can use derivative to help us figure out, well, what is the velocity of that particle? And what is the acceleration of that particle? How much distance has this particle moved, so on and so on. And derivatives are actually really going to help us with that. So we're going to start off with some basic definitions. So the first one is position, because we're going to be using this terminology quite a bit in this learning guide. So the position of an article, or sorry, a position of an object is its location relative to some origin. So basically this is like the distance from an origin specifically. So if I'm looking at the position of something, I want to see where it is in relation to the origin. Position is a vector quantity, which means that it shows both magnitude and direction. Super neat writing today. All right. Now, what are magnitude and direction? So again, if you're not in physics, some of this terminology might not be too familiar. Magnitude is basically how far something is from the origin. And don't worry, I'll give you kind of a visual representation of this in a minute. And direction is talking about the sign of the number. So if I'm looking at basically, just to kind of make it familiar, never eat soggy Wheaties. All right, so we've got our north, east, southwest. If I'm looking at positives, obviously then that would be probably talking about north and east, or it could be forward as well. We'll talk about that a little bit later. And negative, it kind of makes sense then that it would be south and west, or it could be backwards, down, etc. Okay, so distance and displacement, again, are a couple of words that you're going to need to know the difference between. Distance is basically the length of the route between the start and the finish. So we would talk, if we were going on a trip, we would say the distance we traveled was this to this. And that could have included pit stops. It could have included, you know, visiting different landmarks, whatever. Distance is always positive. Okay. And it's a scalar quantity. And what does that mean? Well, it doesn't have a direction. So no direction. So you just say, I traveled this much, or this many kilometers. That's a distance. Displacement is a little bit different. This is the shortest distance between the start and the finish. So it's basically how far did you travel from the origin? Not how far did you travel including your pit stops and the bathroom breaks and whatever. It's just saying how far from start to finish did you actually go. This is a vector quantity. Which means, again, it has magnitude, which we talked about, and direction. Okay? Now, I told you I'd show you kind of like a visual representation of this, the difference between distance and displacement. So for instance, if this was you and you went on a crazy trip all around the country and you ended up over here, everything that I just drew is going to be the distance traveled, right? That's how far your car was actually driving. If I talked about displacement, well, realistically, from here to here is the displacement from your origin. Okay, So just kind of a visual representation of what. Consider the following position time graph. Assume forward is positive and backwards is negative. What is the position of the object at 7 seconds? Well, here's our 7 seconds. So we're down here. Now that's -6. So we're at -6. But what does that mean? Well, backwards is negative. So that means that we're going 6 meters backwards. Okay, at 13 seconds here, well, that's a +4 meters, which basically means 4 meters forward. Okay, all right, let's look at the next one. What is the distance traveled from 5 seconds to 6 seconds? So our 5 seconds is here, up to 6 seconds is here. So what is the distance traveled right there? Well, distance, remember, is always a positive. So even though it's -6, that's kind of what you would see there, we would just say we've traveled 6 meters. From 8 seconds to 11.5, so here's 8 to 11.5 is going to be right about here. So it's this whole distance right there. So I've gone from 6 up to 4. Sorry, -6 up to 4. So we could just say 6 plus 4 is equal to 10 meters. And again, it's just going to be positive because it's a distance. When is the object at rest? Well, again, if positive is forward and negative is backward, something that is stagnant here, not moving, is obviously going to be where our object is at rest. So we would just say 2 to 4 seconds. We could say 6 to 8 seconds and 11.5 to 13 seconds. So again, it's just in those little red areas there. All right, and the last question, when is the object moving forward? Well, remember, forward is positive. So we're looking to see where is our slope basically a positive movement. So it would be here. So that would be from 0 to 2 seconds. And another positive would be, sorry guys, it would be from there to there. So that would be about 8 to 11.5 seconds. And then obviously moving backward is going to be from here to here, where we're going down. So that would be from 4 to 6. And then the last one would be 13 to 16. Okay, so pretty straightforward. All right, now let's kind of figure out how we're using this information. So this first little bit is kind of important. It's saying instantaneous velocity. This is the velocity at one instant in time. So this is what I was kind of talking about at the very beginning, why we're actually going to use this. We're going to bring in derivatives here, and we're going to be able to look at a particle movement or any kind of movement at the graph of that and figure out what is the velocity at one stage. And now that should kind of remind you of when we first started talking derivatives, right? When I want to find the slope at any given point, it's the same kind of thing. So velocity is the slope of the tangent. So again, that should sound familiar. Line on a position time graph. Okay, so velocity is the slope of the tangent line. So what does that mean? Velocity, what is the slope of a tangent line? Well, that is the derivative. So velocity is the derivative of the position time function. And basically we call a position time function S of t. So if I kind of summarize that, because obviously that's a lot of writing, velocity equals the derivative of position with regard to the time. So basically I've got S prime of t. So recall, the first derivative identifies slope. So again, think back to Learning Guide 5 when we were talking about the first derivative and then the second derivative. The first derivative, remember, identifies slope. The second derivative, if you can remember, identifies concavity, and we'll talk about that a little bit later. All right, so let's look at an example of this. Okay, this is more what you're going to see on your assignment and in your textbook. What is the average velocity? So remember, velocity is our first derivative of a rock being thrown up that reaches a height of s equals blah, 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 where t is time in seconds and s is height in meters. So remember, this is my position, and velocity is equal to my first derivative. So all we have to do in this question is take the derivative of this guy here, which is just going to be 24 minus 1.6t. Okay, so this would be our average velocity, how we would find it at any given time. It's saying how long did it take for the rock to reach its highest point? Now when I say highest point, immediately you should think of kind of visually a graph. And at the highest point, we know that that's going to be a maximum. And from Learning Guide 5, you guys should remember that we can easily find maximum and minimums by looking at the critical value. Okay? And remember, how do I find a critical value? I set my derivative equal to 0. So I've got my 0 equals 24 minus 1.6t, and at that stage then now we can solve for t. So minus 24 divided by negative 1.6, t is going to be equal to 15 seconds. How high did it go? Well, this is where I would need to come back to my original position graph. Remember, if I'm looking for coordinates or I'm looking for anything specific according to the movement, I have to go back to that original. Again, that's from Learning Guide 5. So if my maximum has to be here at 15 seconds, how high did it go? Obviously, we're going to substitute that into our original equation here. So that's going to look like s of 15 is equal to 24 times 15 minus 0.8 times 15 squared. And when you evaluate that, you're going to get about 180 meters. So that is how awesome our velocity, how we can find it. We can just take that derivative and we're good to go. So if I take a look here, this is basically our velocity on a position time graph. This is more of a visual representation, which I always like to show. Velocity is, again, the slope of a position time graph. So remember, velocity is the slope on this graph. So if we look at the slope here, we know that from A to B, I've got a positive slope. So A to B, I've got a positive velocity. B to C is a negative slope. So B to C is going to be a negative velocity. Make sense? This C to D is again going to be a negative velocity. D to E is a positive slope. So D to E, right in that area, we would have a positive velocity. Here again, positive, so E to F is going to be positive velocity. And last but not least, the slope here is going to be a negative. So F to G would have a negative velocity. So again, just a very visual way of representing what we were talking about. To summarize so far, because there is going to be a lot of information given in Learning Guide 6, so we're going to do this a couple times. So let's summarize. Velocity always indicates the direction of motion. If the velocity is greater than 0, so if the velocity is positive, then the object must be moving in a positive direction. Okay. And on the graph, this would be a right, it would be forward, it could be up, anything that's going to indicate a positive. Okay. Then obviously if the velocity is less than 0, then the object must be moving in a negative direction. Okay, and on the graph, this would be then obviously the opposite. So it would be left, it would be backward, it would be down, etc. Okay. If the velocity is equal to 0, so think about what that would look like on your graph. Velocity is a slope. So if I have a velocity equal to 0, well, that must be a maximum or a minimum, right? Because my slope is therefore going to be a 0. So that would mean that either, it could also mean kind of like an endpoint in some situations, then the object is either at rest or changing direction. And don't worry, we'll kind of put all of this together in a few questions. And then on the graph, obviously this would be either a maximum or a minimum. Okay? All right, let's take a look at this example. It's saying the motion of a particle is described by the position function, blah, 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 where t is measured in seconds and s is measured in meters. Find the local maximum and or local minimum of the value of s. Now, what I'm going to remind you guys of is back in Learning Guide 5, we talked about the first derivative test, and then there's also a shortcut called the second derivative test. And unfortunately, a lot of students are like, I don't need a shortcut. I'm just going to do it the long way because there's too much to remember. But that second derivative test is amazing. It actually cuts down on heaps of work, and it's very logical. The more you think about it, the more logic-based it is. So I'm going to remind you, I'm just going to say recall, okay, the second derivative test. Okay, and we can very easily find our critical values. And remember, what do we do with those critical values? Once we find them, if I plug that into my second derivative, remember we find the critical values from the first derivative. So the second derivative, if I plug that critical value in and it's a positive, that automatically means I've got a happy face graph, a positive graph, which means that I've got at my minimum, x is equal to that critical value. So it saves having to do those little test intervals, that kind of stuff. So remember, we find the critical value from my first derivative, I plug that into my second derivative, and that automatically tells me if I have a happy face or a sad face graph. Now, there is a little loophole, remember, with the second derivative. If you get it equal to 0, then you have to do it the long way. Okay, so if it doesn't always works, but like 99% of the time it's going to work for you guys. Okay, obviously opposite to that, if this is less than 0, that gives me a sad face graph. That means that I've obviously got a maximum at x is equal to c. Now, if what I just said does not make any sense to you, right now you might want to take a look back in your Learning Guide 5 and review the second derivative test, because that's what I'm going to use in this question. All right, so if we go back to the question, it's saying find the local maximum and or local minimum values of s. So this is actually looking for coordinates here. So I'm going to use the second derivative test. Okay, I'll just do the rest in a different color. So obviously the first thing we need to do is find that first derivative to figure out what our critical values are. So the first derivative, 12t squared minus 14t plus 2. And if I set that equal to 0, okay, to find our critical values, I can basically factor out a 2, and I'm left with 6t squared minus 7t plus 1. Now, I can use my PSA2 method. There we go. And we know it's going to be -6 and -1. So if I rewrite that, 0 is equal to 2 times. I've got 6t squared minus 6t minus 1t plus 1. Factor that all up. So I've got 2 is going to be 6t, and I'm left with t minus 1. Factor out a -1, I'm left with t minus 1. And put it all together. I've got my 6t minus 1 and t minus 1. So very nicely, I can get my critical values from these brackets, and I know t is going to equal 1 over 6 and 1. Okay. Now once I've got these critical values, remember the question is saying find the local max and min. So now is when I'm going to bring in that second derivative test. So first we need to find the second derivative. Okay, so if I go back up here, this was my first derivative. So my second derivative is obviously going to be 24 minus 14. Okay. Now what we're going to do is we're going to plug in those critical values. So I've got t is equal to 1 over 6. So let's plug in 1 over 6 there. So that's going to be 24 basically divided by 6 minus 14. So that's going to give us a negative 10. Now remember, that's a negative. I don't really care about the 10. I just care about the negative. And the negative tells me it's a sad face graph, which, remember, tells me that we now have a maximum at x is equal to 1 over 6, that critical value. Love this second derivative test. Works so well. All right, now the next one is plugging in our 1. So now we've got 24 times 1 minus 14. Well, obviously that's going to be positive. Again, doesn't matter about the 10. Positive is a happy face graph, which now tells us that we've got a minimum at x is equal to 1. Now the question was saying find the local max or min values. So it is actually asking basically for the coordinates. So remember, with the coordinates back from Learning Guide 5, you need to always look at your original graph. Let's do this last one in, again, a different color. So S of t, okay? And we've got, basically, I'm just going to take a shortcut. I'm not going to rewrite the whole thing. We want to find S of 1 over 6. So that would be 4 times 1 over 6 cubed minus 7 times 1 over 6 squared plus 2 times 1 over 6 plus 15. And you guys can go ahead and evaluate that yourselves. And you're going to end up with 15.2 meters. So that automatically gives us our maximum value at 1 over 6, 15.2. Okay, so that's going to be part of our answer. And the next little bit here, sorry, I don't know why this is here. There we go. And our next one is just going to be our 1. So we're going to do the same thing. So 4, 1 cubed minus 7 times 1 squared plus 2 times 1 minus 15. When you evaluate that, you're going to get 14 meters. And that obviously is going to tell us that we have a minimum value at 114. Okay. Now if we move on with this question, you can see that we've got a couple more questions with it. It's saying describe the direction of motion during the first 5 seconds. So describe the direction of the motion. So remember, kind of like right and left is basically what we're looking at, and right and up and left and down are associated with one another. So if I've got, let's just say for instance, I've got a maximum graph. Well, we know that this is a positive, which we can kind of say is basically going to be right or up. They're all kind of associated. This is a negative, so obviously we could say a left, or we could say down, or we could say backward, okay? Just kind of depending on the particle and what's actually happening with each specific question. Okay, so let's take a look here. Now, obviously, this is dealing with maximum or minimum, which we've already talked about, which is really good. So if I look at this, we know that my domain, it said right at the beginning of the question here, and we've repeated it, t has to be greater than or equal to 0. So 0 is a critical value, whether we like it or not. And it's also saying during the first 5 seconds. So that is also going to be a critical value that we need to consider, plus the critical values that we've already determined in A. We've already figured out 1 over 6 and 1, something is happening there. And we've already talked about, okay, well, we have a maximum at 1 over 6, and we have a minimum at 1. So we know that this graph is going up here, and then it's going down because that's our maximum value. And then we also know that it has to be going up because 1 is a minimum value. Does that make sense? So again, we're just looking at maximum and minimums. So we can say, therefore, just by using logic, the particle is moving. Now again, if I kind of color code this, here and here, this is up. So that we can say up, we can say right. So the particle is moving right from 0 to 1 over 6 seconds and 1 to 5 seconds. We can say the particle is moving left, and that would be obviously down. So we're looking from here to here, from 1 over 6 to 1 second. Okay, so we're just kind of using logic for that one. The next question, we're going to have to think a little bit more about what all these critical values mean. It's saying find the total distance traveled in the first 5 seconds. Now, if I'm talking distance, obviously we need to think back to our initial, original equation. We're not talking derivatives, we're not talking velocity, we're not talking anything else. We're just saying what's the distance traveled. Now, again, we need to think, okay, well, how much distance is traveled in all of these little intervals? Because if it's, you know, traveling forward here and then backward and then forward, we don't know. We're going to have to take each part individually. Now, also, we cannot just assume that this is 0. We can't assume that the distance traveled is 0. We have to take a look at, okay, well, what distance are we at when we first start? Okay? Kind of like that first example that we did where we didn't start at 5 meters, we didn't start at 0 meters, we started at 5 meters. So if I'm looking here, basically there was a formula that we used, or a little equation that we used, that was our S2 minus S1. So we're going to consider that here. And again, if I look at this guy, the first thing that we're going to need to consider is that 0. So we're going to do S of 0. Now, I'm going to let you guys do all these calculations. I'm not going to write them all out. When you do the calculations, you know S of 0 is going to be 15. The next one is going to be S of 1 over 6, which we've already determined previously. That's 15.2. S of 1, again, we've already determined that in a previous question. That's going to be 14. And then the last one here, S of 5, you'll need to calculate that one. And when you do, it's going to be 350. So that's where we're at all of those specific points. So if I want to look at the distance traveled, so how far did it get from here to here, well, all we need to do is take that second one and subtract the first one. But remember, distance is always positive. So we can use our absolute values here. Okay? So again, we're taking that second one and we're subtracting the one before it to find that total distance. And again, we're using absolute values because distance is always positive. And that's going to be equal to our total. So I've got 0.2 here, plus 1.2 there, plus 336 here. So our total distance is going to be about 337.4 meters. Okay? Now guys, you can see on your note package that you've got some homework right here. Do yourself a favor and practice that. Again, all the solutions are up on the virtual classroom. Make sure you look, make sure you practice, and see the help desk if you guys have any questions.